Okay, looks like we've got a full house, so I think we can begin. So, hello everyone, and welcome to the 18th Andrew Chamblin Memorial Lecture. My name is Harvey Rial. I'm a professor of theoretical physics here in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. So before I introduce our speaker today, I'd like to say a few words about Andrew Chamblin, in whose memory these lectures are held. Andrew was born in Lubbock in Texas and brought up in nearby Amarillo. After a brilliant undergraduate career at Rice University, he moved to the UK to study for a year in Oxford, where he worked on twistor theory with Roger Penrose. He then moved here to Cambridge to study for a PhD under the supervision of Gary Gibbons and Stephen Hawking. He was subsequently elected to a junior research fellowship at Pembroke College here in Cambridge, and went on to hold postdoctoral positions at several institutions before becoming a member of the faculty at the University of Louisville in Kentucky. Over his career, Andrew produced many influential papers on general relativity and quantum gravity, including one which now has over 1,000 citations. Sadly, Andrew died unexpectedly in 2006 at the age of just 36. Following his death, his friends and family established this lecture series in his memory. So the first Andrew Chamblin lecture was given by Stephen Hawking, who was followed by many more very distinguished speakers. And you can find recordings of many of these talks on our website. So now let me introduce our speaker. So Andrew Strominger received his PhD from MIT in 1981. He held a postdoctoral position at the Institute for Advanced Study in Princeton. And then after a faculty position at the University of California at Santa Barbara, he joined the faculty in Harvard, where he is now the Gwill E. York Professor of Physics, the founding principal investigator of the Black Hole Initiative, and the director of the Simons Collaboration on Celestial Holography. In his research, Andy has endeavoured to shed light on the unsolved problems in the fundamental laws of nature. These problems include the unification of forces and particles, the origin of the universe, and the quantum structure of black holes. His work on these topics has earned him several prestigious prizes, including the Breakthrough Prize in Fundamental Physics, the Danny Heinemann Prize, the Physics Frontiers Breakthrough Prize, the Dirac Medal, the Oscar Klein Medal, and the Leonard Eisenbud Prize. So please join me in welcoming Andy to deliver the Andrew Chamblin Lecture this evening.
Thank you for the kind introduction, Harvey. So I'm going to talk about black holes. And as you've already heard, this is the Chamblin lecture, and you probably know you're in Cambridge. So it's a special honor for me to give this lecture. I knew Andy, I'd say well, when we overlapped. We were at Santa Barbara the same time, a long time ago now, 20 years ago. One of the things various of my friends, Cliff Johnson and Amanda Pete, who were also there at the time, I didn't have a camera, but they sent me some of their photos, and you cannot find a photo of Andy except maybe this one, where he's not smiling. I don't know if that's a smile or not. It looks like he's about to smile. And he was a wonderful human being. He loved physics. He was always fun to be around, and we miss him. And here's a picture of him with his thesis advisors on the beach at Santa Barbara, Stephen and Gary. Here, I think he's trying out for the Blues Brothers. I don't know what's going on there. That's with Don Meroff, and that's an earlier picture. Let me also say it's a pleasure for me to be giving this lecture in Cambridge. I love Cambridge. I was actually born here, never lived here, but I was born here, been back many times. There's no place in the world like Cambridge. You notice that very much if you don't live here. There's just such a wonderful sense of first of all, the antiquity, but also the preeminence of searching for knowledge as what one does in life. I don't think it's valued anywhere else on the planet the way it is in this city, and it's a wonderful thing to be here. Oops, okay, I have to use this. Why is it doing this now? Okay, there. Okay, so condensed matter physics, like astrophysics, studies systems with many, many different components. And back in the 17th or 18th century, the study of condensed matter physics was you took your favorite compound or milk or oil or whatever, and you heated it up, you put some gas under it, saw how much the pressure rised, and you studied properties of condensed materials, and it was a huge library of factoids that had no particular organizing principle. But by now, condensed matter physics is very different. It's organized around the principle of critical phenomena, and I'll say what that is in a minute. And general systems are regarded as perturbations around special critical systems. And critical systems appear in extreme or special situation in which matter exhibits critical behavior. And often in these extreme or special situations, you can solve the system exactly. And examples of critical behavior appear, well, low temperatures is a big one, or at special tuned values of magnetic fields, near phase transitions, or other places. And it's often found that at these special points, under these special circumstances, there are extra symmetries that appear, and it's precisely the appearance of those symmetries that enables the system to be solved exactly. So the classic example discovered observationally by Thomas Andrews, probably at Cambridge, I don't know, in 1869, is the critical opalescence of the liquid to gas phase transition in carbon dioxide. So carbon dioxide, it's transparent unless you're exactly at this special combinations of pressures and temperature. And then when you're about to make the transition from liquid to gas, and what happens there is that there's a symmetry of relating things of all different scales. Ordinarily, there's a scale in the system, the intermolecular spacing. But here, there's a symmetry that is across all scales. And since all scales are involved in the dynamics of carbon dioxide at this phase transition, it can absorb light at any scale. So you tune it to that temperature, and all of a sudden, you have the light behind it, and all of a sudden, it just goes black. A very simple experiment to do. And this also illustrates another fact, that systems at critical phenomena, at critical behavior, often exhibit very observationally striking phenomena. Now, condensed matter physics, of course, is a very old subject because you've been able to put things on the table and play with them and get them into these critical configurations easily. And by comparison, astronomy and astrophysics is a new subject. There's been, especially in the last couple decades, there's been a huge increase in the precision with which we can observe the sky. But really, as a science, it is still behaving like condensed matter 100 years ago. I mean, rightly, that's what should be doing now, but just cataloging what you see in the sky and not so much an organizing principle. But it's beginning to appear critical behavior in the sky, in astronomy, has already been beginning to appear. And the most important example of that is the theory of inflation. And the theory of inflation poses that if you go back to very high redshifts, which again we can think of as low energies, and even in condensed matter system, the analogies get mixed up in a very beautiful way. In condensed matter physics, you might want to put a system to low temperature to see the critical behavior, but in gravitational systems, you might want to put it at high redshift, which is, of course, related. Now, so if we go to very high redshift, and that is the very early universe, there is, it is posited that there is a de Sitter, inflationary de Sitter regime of space-time. And that is a classic example of critical behavior. And de Sitter, the group of de Sitter space is what we call a conformal group, and it has an element that changes all the length scales. And that the main prediction of the inflationary theory, namely the simple variation of the size of the fluctuations in the cosmic microwave background, is a simple prediction of this symmetry. So in fact, you don't really need all the discussion of de Sitter space and so on to get this prediction. Quantum gravity could be strongly coupled there. Maybe there isn't any space-time. As long as you have this enhanced emergent symmetry as a result of going to the big redshift, then you get all the wonderful astrophysical results that we want. And this symmetry group that de Sitter has is the so-called conformal symmetry group of the three-dimensional plane. It says that there's no scales there. Okay, so that is a well-understood thing, though they typically don't use the language that I just used. But what I'm going to talk about now is the critical behavior of black holes, which occurs in many different guises. And it occurs in extreme Kerr black holes. It occurs at the so-called photon ring, which we're hoping to see. And moreover, it's played the central role in a very different kind of enterprise to understand black holes. That is, to understand the quantum puzzles of black holes that were brought to us by our friend Stephen Hawking. And in both of these, in all of these, critical behavior is important. So I'm going to start, now there are people here from young children interested in black holes to some of the people who you could almost say invented the subject. And I'm going to hope to have something for everybody. And I'm going to start with kind of a review of the crazy history of black holes, which we are still in the middle of. So Einstein discovered his field equations in 1915, and it said that he thought nobody could solve them exactly. But Schwarzschild did so only a few months later, and he found the solution we now call the black hole, though that name came 50 years later. And it was so confusing. People always ask me, why haven't you guys figured this out yet, the quantum behavior of black hole, But it took 50 years, and I guess really Penrose just got the Nobel Prize for it. It took 50 years to understand what a black hole was before you put quantum mechanics in. And just to underscore that, Einstein wrote a paper in 1939, that is, 25 years after Schwarzschild, in which he said that black holes didn't exist, and made a statement for which he would flunk any respectable general relativity course, certainly including the ones that are taught here. And so this was very confusing. Already in the 70s, where I live, 70s, 80s, even 90s, people were saying, okay, black holes don't really exist. Yeah, maybe we found the solution, but we're never going to, or if they do exist, we're never going to see them. Who cares? This was an attitude which was there, I think, when I was a graduate student in the late 70s, early 80s. Most physicists outside of Cambridge thought that, this Cambridge, thought that black holes didn't exist. And of course, it's all changed now. Now, what was this classical story? Well, you can say that a black hole is the horizon is the edge of space-time. And inside the black hole, there's nothing. And if you throw into a black hole, this is kind of the classical picture of black hole, it just sort of dissolves. If you throw a penny into the sun, that penny will melt, of course, and it'll be spread around. It'll make little itty-bitty changes in all the molecules in the sun. But if you throw a penny into the black hole, they're perfectly round. Well, they can spin, but they're kind of perfectly, some penny into a black hole. It'll burp a little bit as it goes in, but then it will settle down to the same featureless thing. And that was described by John Wheeler as saying that black holes have no hair. Okay, so the classical story of black holes was well understood, I would say, by the early 70s, when you don't include quantum mechanics. And then there was a huge surprise. We don't really know what's inside a black hole, except for sure they're full of surprises. We keep learning new things about them that we hadn't expected. And in 1974, Hawking showed that black holes evaporate, and moreover, they evaporate with a very particular spectrum given by the Hawking temperature. And this can be thought of as the uncertainty principle, the little photons popping in and out of the vacuum. The horizon is fluctuating. We don't quite know where the horizon is, so they can kind of sneak out quantum mechanically. And this formula is what's called a thermodynamic formula. So thermodynamic formulas are things that people have been studying for hundreds of years. It's how the temperature, if you add some energy, how the temperature will raise and so on. And thermodynamics is a very, very old subject, much older than black holes or quantum mechanics. So it's a thermodynamic formula. And in a very beautiful development in the 19th century, Boltzmann showed that thermodynamic laws of that type can be understood just using statistical reasoning and the assumption that everything is made of molecules. And this, of course, is one of the most spectacular developments in all of science. And a central notion in Boltzmann's construction is that you fix the energy or something, and you count how many configurations of the system there are. And then the system seeks its most, from that number, obviously I won't go through this, but from that number, the system seeks its most probable configuration, and that accounts for the behavior of materials, their pressure, how fast they heat up, what happens when you mix them, and so on. So, I've just told you about two great formulas. As far as I know, there are only 4 formulas that people were so proud of that they had it put on their headstone, and these are 2 of them. Well, why did it do that this time? Okay, let's play. These are 2 of them. Stevens' formula for the temperature of a black hole, and Boltzmann's formula for the entropy as a function of state, of the number of configurations of the system. And put those together, and you can compute the famous Bekenstein-Hawking formula for the number of kilobytes of information storage capacity in a black hole. And it's a very mysterious and a very universal formula. Unlike other formula that have come along in the history of physics, so you have Maxwell's equations, which tell you about the electric and magnetic field. You have Einstein's equations, which tell you about the gravitational field. You have Boltzmann's equations, which tell you about statistics of systems with many bodies. This formula gets its fingers into every major field of modern physics. It's quantum, it's got an h-bar, it's got gravity, it's got Newton's constant, it's got geometry in the area of the black hole, and it's got statistical mechanics because it has Boltzmann's constant in it. So it's really kind of an uber formula, and it seems to have very wide applicability. We just infer from consistency in a large variety of situations, but exactly what it's telling us, we don't really know. It's also very big. So all the information in the Google data banks, if you would fit into a black hole, that's a trillionth of a trillionth of a millimeter. So there's really a lot of stuff that you can put in there. We think, and indeed you would have contradictions if you assumed otherwise, that this is an upper bound on how much, and this is related to what's called the holographic principle, this is an upper bound on how much information a given region of space-time can hold. And so just to relate this to other things you've heard, there's something called Moore's law about how much information you can put on a computer chip, namely that it doubles every 3 years, and if you just work the numbers, you'll find that in 300 years, our cell phones will all have little black holes in them. And then there will be no iPhone 1,000,000,001, because that is as good as you can do. Okay. So this brings us, if you've been listening carefully, I've told you some things that are diametrically opposed to one another. One is that there's nothing in a black hole. They're featureless holes in space. And the other is that they're the most complicated objects in the universe. So this is a really important puzzle in modern physics. It's obviously telling us something about, because to get to this second picture, you need to use h-bar. That formula had quantum mechanics in it. You needed to use the Hawking radiation formula. And who would ever have thought before 1974 that the then already well-noticed problem of consistently putting together quantum mechanics and gravity would somehow involve black holes. They seemed like orthogonal problems. But there we are. Now, now this is understanding a black hole as a statistical object. There's a yet further and more terrifying puzzle called the information puzzle of what happens when the black hole evaporates to all the information that went inside it. And that is also, Stephen himself suggested, but later retracted, that information was destroyed, but we actually don't know yet. Now, some insight into the puzzle, and this is telling me where to go next, was, I'm not going to really say very much about string theory, but some important insight was gained in the mid-90s in which a particular kind of so-called supersymmetric black holes in a universe not necessarily our own, described by string theory, for such black holes, there's been a really fantastic amount of detailed understanding and very powerful computational tools for describing things that happen in universes which are described by string theory. And those universes also have the information puzzle. And we can use the computational power in that context to see how the puzzle is evaded, and in particular how the microstates are counted. And what was shown with great precision is that there's a kind of holographic plate that lives around the black hole. And I'm calling it a hologram because it has one dimension less than the black hole itself. It lives there, and it has all the information about the black hole is carried on its surface and can be very explicitly counted, and it works perfectly. So we understood in this context where, in this stringy context, where the microstates that Boltzmann needed to compute the thermodynamics of black holes resides. Now, that was very exciting and led to many developments and so on, but I would like to know where the microstates for M87 or Sag A star live. And I don't think I'm going to live long enough to, I think I might live long enough to answer that question, but I don't think I'm going to live long enough to figure out whether string theory describes our world or not. And so now, so the way this works is it seemed impossible to find a way that black holes could be associated with some microstates. String theory used a clever trick. The real world could use the same trick. Now we know a trick that makes everything consistent. Maybe the real world uses the same trick or some variant of it, and so that's an interesting direction to go. And one of the things that was understood that made this stringy calculation actually very simple in the end, if you set it up the right way, is that the key ingredient that made everything work was some critical behavior and the appearance of conformal symmetry. And this conformal symmetry actually appears right near the horizon of the black hole. What is conformal symmetry? Okay, so this is an example of, actually I got this from a hypnosis thing on the web. I'm not trying to hypnotize anybody. But This actually is exactly what conformal symmetry is. It's something that looks the same on every length scale. You keep zooming in and zooming in on a more powerful microscope, and it just, why did it stop? Yeah. You keep zooming in on a more powerful microscope, but no matter how far you go, it just looks exactly the same. So there are black holes that have exactly this kind of behavior near the horizon. If you move in a spatial direction towards the horizon, then, oh, it only goes for a finite time, I see. If you move in a spatial direction near the horizon, it just keeps looking the same. And it's also true in the early universe, in the de Sitter story, you move back earlier in time. As you get to earlier in time, you get a self-similarity, and the space-time you're in just keeps looking the same, even though you're moving. Okay. Now, it turns out that this conformal symmetry exists in a special kind of black hole. So black holes can have spin, and there's a speed limit on how fast a black hole can spin. The horizon can't go faster than the speed of light. And with such a black hole, as you get closer to it, it's self-similar. It's just like that picture. And now, surprisingly, such things are extremely common, much more common than they would by some random, by just random distribution of spins. There are a lot of black holes there with very high spins that have been measured with, whose spin, they've been measured, and they just, a lot of them end up to have very high spins. So this conformal symmetry may be actually a good approximation for some of these black holes. Now, we'd like to actually talk about the observational symmetry of, we have a symmetry, the symmetry is related to understanding the microstates responsible for the Bekenstein-Hawking entropy for Kerr black holes, but we'd also like to see it observationally. And so we wrote some papers on that, the polarimetric images. It doesn't look too promising for either the Event Horizon Telescope or even the next generation Event Horizon Telescope. Too faint by sort of 3 or 4 orders of magnitude, not just a factor of 2. It's quite possible that we'll be able to see this conformal symmetry. The larger black holes tend to be even closer to extremality because they've had a long time for stuff to fall in, and when stuff falls in, it spins them up. And this sounds, to anyone who's worked in condensed matter physics, this is the typical thing that happens. It's called an attractive fixed point. You interact with your environment, and it pushes you closer and closer to your fixed point, and that's exactly what happens with black holes. They get pushed to this extreme value. Might be able to see some of these, I'm not holding my breath, but it might be with extreme mass ratio in spirals at LISA, which is the next generation gravitational, space-based gravitational wave detector. So that could happen, but not soon. However, there's a completely different and unexpected appearance of conformal symmetry that we understood only recently around black holes. And this came about when, at the Black Hole Initiative, where I'm a PI, when they where my observational friends there, in particular Shep Dolman and Michael Johnson, took this incredible picture that I think changed the way that everybody thinks about black holes, and we started a conversation with them about what could we see. One of the difficulties, frustrations with this picture is that even if you improve the image, you might not learn that much about the black hole. You might just learn, the chemical composition or what of the stuff that's circulating around the black hole. And you really want to see the geometry of space-time. You don't want to learn about, you do, depending on who you are. But I want to learn, and many people want to learn about the geometry of black holes. And so we started talking, and we realized that there was a really interesting thing that happens around black holes, that there's an emergent conformal symmetry around something called the photon ring. And this one, we may have hit the jackpot with an observation. It looks like we're going to be able to see it, and for the first time see conformal symmetry in black holes around the sky. So what is this? Well, this story is the photon ring. So suppose this is me, and there's a black hole right here. You'll see my direct image, but you'll also see an image where light came from me and swerved around behind the black hole, and you'd see it over there, upside down. But it could also go in front of the black hole and swing around 360 degrees and come back up. Then it won't be reversed. And in fact, it can make any number of half orbits. And these half orbits all converge on a line, a ring, the so-called photon ring. Similarly, an image from inside the photon ring, but outside the black hole, will also be a sequence there converging from the inside of the photon ring. These are self-similar images, and there's actually some beautiful math behind this that turns out that each of these photon rings is unstable. It has what's called a Lyapunov exponent that tells you how unstable it is. And that Lyapunov exponent is related to the relative luminosity on the subsequent rings. And this Lyapunov exponent depends on a very detailed way on how the black hole is spinning, or if it has charge, or anything. So basically, these rings encode all the information about the geometry of the space-time in a very scrambled up and interesting way. Now, here's another picture of what we hope to see. So the black hole is in the middle there. And that's images not deflected. There's images deflected halfway around. Here's going a full orbit. That makes a different image. These are all different consecutive rings. And at the end of the day, this is what we will see. And in the picture that they took of M87, this could not be resolved. It wasn't, the resolution wasn't good enough. If you like, they had maybe 20 pixels for the whole picture. So we need about a factor of 10. Now, the really beautiful thing is, that happened is, so when I first calculated this, okay, I'm like, okay, this is a theorist's pipe dream. You know, these little rings in you know, hidden in this bright image, and subsequent rings, which I drew them on the cartoon far apart, but in space they're right on top of it. It's a theorist's pipe dream to try to see this. But the point is, these experiments are done with VLBI, and VLBI really measures in Fourier space. And in the original VLBI image, which isn't what you've seen all over the newspapers, it's the Fourier transform of that, these things are completely disjoint. What do you need to do to see these? You need to see higher frequencies, which is longer wavelengths, which means we need a radio telescope in space. Now, how far in space? Okay, for me, it takes a long time to work out these numbers. It could have been the next galaxy, could have been the top of the Empire State Building. Turned out that to line up beautifully with what is observationally possible. So the first ring, we're going to, it's already pretty well planned out. The first ring we're going to see low Earth, a satellite mission at low Earth orbit. The second ring, to see the n=2 ring, we go to the moon. And then the n=3 ring, we can go to L2, where the Lagrange point where the James Webb telescope is now. So we really got lucky this time. We found some theoretical phenomena that agrees with that we, of conformal symmetry, where we're actually going to observe it. Okay. And now I am going to set up my live photon ring. Okay, there you go. Okay, I'm going to get out of the way in a second. You should all be able to, you should all be able to see yourselves many times. And if you had a really, really good telescope and you just looked at M87, this is what you would see. So watch what happens. Let's see, I'm going to wave. Oh, I think I need to, I've got to point it too much this way. I'm going to wave. You see, there I am, right side up on the left, upside down on the right. I encourage everybody to wave and see if you can see yourself. Yeah, and the different images are related by conformal symmetry. And it's actually a much more complicated action of conformal symmetry. The black bands in that picture are this was made for me by my student who's graduating now, Dominic Chang. And you need a 360 camera. If you have a 360 camera, you can fill in the black bands. And also the code is harder to write. But anyway. So that's what we're hoping to see. And now, this conformal symmetry is not, well, an open question is, could this conformal symmetry be related to understanding the microstates of rotating black holes? We don't know the answer to that question. Okay, so what is being planned now? So what already happened was the EHT, the Event Horizon Telescope, wanted to see M87. And to see a small object in the sky, you need a big telescope. Actually, it's the ratio of the baseline of the telescope to the wavelength that you're observing, but there's limitations on which wavelengths can be observed. So you need a big telescope to get a small resolution. And already, 30 or 40 years ago, people roughly knew how big M87 was. And just doing a simple back of the envelope calculation, you needed to use the whole Earth to get the picture. Now, people wouldn't be too happy if you covered the whole Earth with a radio dish, but you can do something just as good, which is you can take the different telescopes on Earth and you can synchronize them so that the images are seen at the same time, and that effectively gives you longer wavelengths. And so in order to see more, in order to see the photon ring, that's the next, or a next step in this expanding observational black hole astrophysics. I think a very interesting one. You need to have an even longer baseline. So our current mission calls for a satellite, a dedicated satellite mission at about 17,000 kilometer orbit. There's a lot of it's a lot of very complicated aspects of this problem. So in order to do this problem, a lot of data involved in taking these photos. In fact, this EHT experiment couldn't have been done 10 years earlier. You wouldn't have been able to get the data back and forth. And they didn't synchronize the data over the internet. These guys went down there with suitcases, put the hard drives in, brought them to Cambridge. It was quite a feat. Now, so one of the big problems with having a space thing is we have to get the data down from space. So we have to beam down with a laser beam 20 gigabytes per second. And we have to carry the capacity for doing that out in space. Obviously, I don't know anything about these things. I know a lot about black holes, but my friends working on the hardware seem to think that everything is lining up. There's no obstacle to actually doing this experiment, so very excited about it. So conclusions. I want to conclude with a quote by Jim Bardeen, one of the great general relativists. He was one of the, these photon rings have been studied in or geodesics, motion of light in the Kerr geometry, of course, has been studied since Kerr discovered the Kerr solution in 1963. But even in Schwarzschild, Hilbert did some calculation which could be construed as having discovered the bound photon orbits back in the 20s. There have been various developments on this. But Jim Bardeen did really a lot on it. And he just started working on it and just thought it was a beautiful, beautiful, mathematically beautiful problem. And couldn't stop working on it because he liked it so much. But he says, it is one of his notes, it's a conceptually interesting, if not astrophysically important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. And it's Bardeen's geodesics, which is exactly what we're hoping to compute. And I think that should be encouraging for all of us who pursue knowledge and more learning about the universe because it's beautiful. And it's exciting that this line of developments is now circling around, theorists and observers are circling around the same set of ideas. It's certainly invigorating for the subject, and the photon ring is a promising next step as we go into our, well, we're well into, as we get into our second century of trying to understand what a black hole is. So I'll stop there, and thank you.
Thank you very much, Andy. That was amazing. So as you said, this is a very diverse audience, ranging from experts to some very young people. And I think you did a great job of making it accessible and entertaining for everyone. So thank you. We have time for questions. Who would like to ask a question? Yes.
How does the mass of the black hole at the centre of our galaxy compare to the mass of everything else in our galaxy?
The mass of our black hole compared to everything else in the, okay. I don't know that number. I'm sure somebody here does. I think it's more by a lot. Is that, no?
It's tiny.
It's what?
It's tiny compared to the rest.
It's tiny.
Yeah, very small fraction.
Okay.
The black hole is 4 million solar masses.
It's,
there are more than 4 million stars.
Yeah.
it's tiny. Its entropy is more.
It's actually one of the positives how it affects the rest of the galaxy. It's so small and mass.
Further questions?
Thank you, Professor. Thank you, Professor, for such a wonderful talk. My question is regarding the holographic one-dimensional surface on the horizon that you mentioned about. So the black hole evaporation occurs from the surface, from the horizon, right? And you mentioned that the information as well is on a one-dimensional holographic surface. So when the black hole evaporates...
Let me correct that in a subtle way. There's a picture in which the information is sitting near the surface of the black hole.
Mm-hmm.
That doesn't mean that has absolute truth. There might be other descriptions that put it in different places.
Okay. I see. So in particular, in that perspective, what would happen to the information, like when the black hole evaporates? Does it have any consequence?
Well, the picture would be, so let me just go back here. Can't do it with this. So actually, if you go back here, to the area law, just the fact that there's an area law is very strange. if you want to know, if I want to know how many gigabytes I can put in my iPhone, it's not the area of the iPhone. If I made it thicker, I could put more chips in it without increasing the area very much. Rather, it would go like the volume. And so it's very strange, it's very striking that the information content is going like the area. It suggests it's all happening on the volume, on the surface, not in the volume. But we don't know how to, except in very special, and it is very reassuring that in very special, highly controlled, stringy mathematical contexts, we can make statements like that mathematically precise. But we don't know how to make them, we don't know how to generalize those precise statements to our own universe, and we don't know, we don't know how they make them. But the idea would be, I think that the picture is that, imagine you tie, roughly speaking, you would get this law if you had chips sitting on the horizon of the black hole, one per Planck unit, roughly. One every 10 to the minus 30 chips sitting on the black hole. Now, of course, they can't sit on the horizon of the black hole because they get sucked in. And if you get in a spaceship now and you go to the middle of the galaxy and you cross the horizon of Sagittarius star, you won't notice anything. There's nothing there. It's not like there's a scaffold at the horizon of the black hole to put chips on. So it doesn't really make sense to say that there's chips there. Still, let's ignore that and let's imagine there's some way of looking at things, that there are chips on the horizon. Then the idea would be that as the black hole shrinks, some of those chips are going off and taking the information off with them. They're dissolving out into the, that would be the stupid picture, which probably has some truth in it. We think. It's too stupid to be wrong.
Thank you for the lecture. And, so my question is, the picture of observing the Folsom ring that you have described seems like a purely classical, general relativistic phenomenon. Could you explain why do we think it could be related to the quantum and statistical physical phenomena of black hole information and temperature and entropy, if the calculations behind it seem purely classical and deterministic?
Well, that's a question. That's a question that isn't even well formulated enough. I wouldn't be able to formulate it well enough to have a research problem. It's more that it smells like that. We know that in a very precise way how this other kind of conformal symmetry, like the one near the extreme Kerr or the one near the stringy black holes, we know in a very precise way that that is telling us exactly what that's telling us. And in the supersymmetric case, there's proofs, and in the Kerr case, there's plausible conjectures about what this is, how this is related to the black hole microstates. Here, it's a new thought that's been circulating around for the last few years, that we've had this kind of roadblock. Some problems have been solved, but what might have seemed the simplest one, the original Schwarzschild black hole, can somebody just give us some picture of how that might work? And the idea that's, I think it's pretty clear that the properties of the photon ring constrain how that could possibly work, because any model that describes the guts of a Schwarzschild black hole, or one that isn't spinning, must reproduce the properties of the photon ring around it. So it's something interesting to think about, which, and I also think it's very interesting because, as some people in this room know, I've been working on black holes a long, long time. And until I was working with these observers, and I hadn't really thought much about the photon ring and what its properties were, and the discovery of this conformal symmetry is a new thing. And so it's an example of how observers and theorists interact without it being so, I mean, in this case, there is a do the experiment, here's the theory, do the experiment, verify it, but often it's more indirect. So it's more an avenue to explore.
More questions?
Thanks very much. I wonder if you could help me with some confusion. I think you said that information is conserved, cannot be destroyed.
Did I say that?
Well, I thought you mentioned that when you talked about getting the information within a black hole and black hole evaporates.
Well, it looks, the black holes call it into question. And I think I said Stephen said that. Oh, no, Stephen said it was destroyed. And then the idea that it was destroyed ran into so much trouble, and the idea that it wasn't destroyed seemed to be accumulating circumstantial evidence, and most people have gone the other way. But the issue is not settled.
Okay, because my question was, if information, why does information have to be conserved? Because if information is conserved, that sounds rather like a deterministic universe.
Sounds like what?
A deterministic universe.
Yeah.
If all the information is always there, I could always work out what happened in the past in detail and go forward. But I thought quantum mechanics said that that's not true.
Okay, that question is easy to answer. Quantum mechanics is deterministic, full stop. What's confusing about it, why people get confused about it, is that the thing that is determined is not what we would naturally think of as classical observers. It's not positions and velocities, it's the quantum state itself. So if you know the quantum state, which describes the results of any experiment you can do now, and you know the laws of physics exactly, you can get it at any time in the future. So quantum mechanics is deterministic, albeit the observables are not what we thought the true observables of nature are not what we thought they were. But the thing that can be determined is. Now, the suggestion about black holes was something much more radical, that if you know the quantum state initially, you can't even get that. And that's the thing which seems to run into irreconcilable difficulties. But you never know till you solve the problem, and it hasn't been solved.
Oh, thank you. Yeah, my question is about on the pictures you showed us, the photon rings and the picture of the black hole from like 5 years ago. Why is there like a shinier side than the others?
Are you talking about this picture? Oh, wait. Where's that picture? This one?
Yeah, and also on
Okay.
the
Very important, very important. They thought, the observers thought they'd seen the photon ring, but they didn't know what the photon ring was. And this is not the photon ring. This is just the direct emission from the accretion disk. And the photon ring is a bound orbit of a photon it's a bound orbit there. And it seems like somebody even wrote a paper, somebody in the EHT collaboration, that if you look at the data the right way, you could see the photon ring, but nobody believed it. So the photon ring hasn't been seen. It's not that far from being seeable, but it does seem that you need to go to space to see it, because we've covered the Earth and there's no way of really getting enough increase to see it. And of course, ultimately we want to do much more than see one photon ring. We want to see the whole, and that will be hopefully an ongoing program in astronomy. And NASA seems to be extremely excited about it. So it's looking promising that it will.
Thank you.
Hello, thank you for the lecture. I wanted to ask about the information. Does information still get lost while the black hole lives? And the information on the horizon, or wherever it is, does it get replaced by other information, or does it stay there till the black hole dies?
Well, I think what most people suspect but don't know is that no information ever gets lost, that black holes are fully quantum mechanical systems, and where information is in a quantum system is a subtle question. It can be sort of in several places at once. That's quantum information theory.
So when the black hole dies, you said the information gets destroyed or not?
Well, the thing that most people would put their bets on is that by the time the black hole has died, but not everyone, but that by the time the black hole has died, the information is outside of it.
Okay. Thank you.
Okay, maybe one last question.
Thank you for the great lecture. My question is still more about the information theory. At this stage, do we know how information is stored in black hole? For example, in other systems, they're stored by probability distribution of dynamic of molecules or by superposition of quantum states. But do we know that how it's stored in black holes? And going back to the slide which says simple and complex, two black holes there, the unit there is k bytes millimeter or something, rather than more intuitively the volume.
Let's take one question at a time.
Okay, yeah.
So the first thing is, it seems very likely that the information is stored in a highly quantum form. You take it's a quantum computer. The pieces of the black, certainly there are examples in string theory where we can look at this, and there it's, so the black hole is really like a quantum computer. Yeah.
Okay, well, thank you everyone for all the great questions, and let's now thank Andy again for a truly fascinating